Let's look at section 2.6, non-measurable sets, from the 4th edition of Royden and Fitzpatrick. This is a bit of a brief version of section 2.6. The version in the 3rd edition I like a little bit better, and there's a few more details in the video on section 2.6 from edition 3. Same material. The proof here looks a little bit different. The concept behind it is exactly the same. It's the Vitali construction of a non-measurable set, quote unquote, on construction, because we'll use the axiom of choice, just like in the 2.6 from the 3rd edition. Okay, so again, it's the Vitali construction. We'll assume measurability of a certain set, and we'll use countable additivity and some translations to show that that leads to a contradiction, and so we don't have measurability of this particular set. The difference in this and what's done previously in the 3rd edition really is, and there they introduced this circle plus stuff, and they kept everything a subset of the interval from 0 to 1. Here they're using boundedness. So boundedness has sort of replaced the subset of the interval from 0 to 1. But conceptually, we're doing the same thing. Lemma 2.16 says, let E be a bounded measurable set of real numbers. Suppose there is a bounded countable infinite set of real numbers, lambda, for which the collection of translates of E plus lambda, where lambda ranges over this countably infinite set of real numbers, also itself bounded, such that this collection is disjoint. Then the claim is the measure V must be 0. So we're taking a bounded measurable set E and a bunch of numbers. Countably many, though, we'll use rational numbers in what's to follow, as we did in section 3.6 in the previous edition. But here, simply an assumption of a countably infinite collection of real numbers that form a bounded set. So there's boundedness all over the place in this. This is, like I said, this is replacing the interval 0, 1 idea from the 3rd edition. And then we have the supposition that E plus lambda, as lambda ranges over that collection of countably many countably many but infinite collection of real numbers forming a bounded set. That creates a disjoint set, then the measure V is 0. Okay, so let's look at a proof of that. All right. We know translates of measurable sets are measurable. Proposition 2.10 early on. We have a hypothesis that set E is measurable. There it is. Set E is measurable. Okay, so all these translates of set E, all these E plus lambdas are measurable as well. We've hypothesized disjointness in this collection of translates. So if we'll union all these together, that is, take a union over those real numbers, those lambdas in capital lambda, whatever set of countably many, this is a countable union, countably many real numbers, bounded in some sense. The union of those E sub lambdas is lambda ranges over all its values. They'll be disjoint, hypothesis. So the measure of the union is the sum of the measures, countable additivity. Yeah, under the assumption E is measurable, so that E plus lambda is measurable for all those lambdas. So countable additivity we have going for us in that situation. Set E is bounded. That set lambda of countably infinite number of real numbers is also bounded. So when I take set E and I add lambdas to it, this will yield, when I union it up, say, this will yield also a bounded set. E has a lower bound and lambda has a lower bound. So those together will determine a lower bound on the union. E has an upper bound, lambda has an upper bound. Those will determine an upper bound on the union of the translates. So we've got boundedness there. Monotonicity would tell you that a bounded measurable set has finite measure. So the boundedness yields finite measure. Measures translation invariant. The measure of E plus lambda and the measure of E is the same. So actually all these have the same measure. If you've looked through the video from the third edition, I recommend going through that before this. You can see some similarities starting to develop now with the proof that we had there. So we've got boundedness, finiteness in terms of the measure of the union of these sets. We've got it bounded. Monotonicity tells you finite measure. We saw above that the measure of the union is the sum of the measures. We had the countable additivity and the disjointness. And translation invariance tells us the measure of E plus lambda is the same as a measure of E, and that holds for all lambda. So here's what we've got. We've got an indexing set capital lambda that's countably infinite. So this summation here is the constant, the number, measure of E, plus a measure of E, plus the measure of E, dot, dot, dot. An infinite, countably infinite number of copies of the measure of E. And we know that that's bounded. Well, the only way that can be bounded, an infinite number of copies of the measure of E. Measure of E is greater than or equal to 0. Measure of E must equal 0. That's claimed. So we must have the measure of E equals 0 since we get the boundedness on this infinite sum of the same values. Again, an idea we ran across in the third edition of the book. Okay, back to the notes for a little bit more commentary, also overlapping with the third edition. For any non-empty set E of real numbers, we'll define an equivalence relation. 2 points in E are said to be rationally equivalent if their difference is rational. Two real numbers differing by a rational are rationally equivalent. This is, in fact, an equivalence relation. Easy to see that it's reflexive, symmetric, and transitive. Just as in the third edition, we've introduced this equivalence relation to partition up a set. So any non-empty set of real numbers could be partitioned into equivalence classes using this equivalence relation. Remember, equivalence relations partition sets into equivalence classes. That's usually what you use equivalence relations for. Partitioning the set means breaks it into pieces which are disjoint and union to give the whole set. That's the meaning of the word partition in this setting. Okay, we're toying around with the axiom of choice now. We're approaching it slightly differently from the third edition of the book, but when all the dust settles, we'll be in the same place. Let E be a non-empty set of real numbers with rational equivalence as an equivalence relation on E. A choice set, so we're defining a choice set, that word choice coming from the axiom of choice, is a set C sub E, a subset of the set E on which the equivalence relation was defined, such that C sub E contains exactly one element of each equivalence class under rational equivalence. Okay, so we've got these equivalence classes. We're reaching into an equivalence class and choosing a representative of that equivalence class. We're reaching into another equivalence class and choosing a representative, and taking all these representatives and throwing them into this set C sub E. Who says you can do that? Who says you can make a set like that? Why, the axiom of choice. So a choice set exists by the axiom of choice. It's page 5 in the fourth edition of the book. I put together a supplemental video on a little bit of history of the axiom of choice and some implications of the axiom of choice. But the axiom of choice guarantees the existence of a choice function, is how we worded it in some of the other settings. And that choice function is what is used in creating the set C sub E. You're choosing representatives from equivalence classes. For additional details, see my supplement on the axiom of choice, and also pretty good, my version of 2.6 from the third edition of Royden's analysis. The choice set C sub E satisfies the following properties. The difference of 2 points in C sub E is always irrational. If 2 points in C sub E had a difference which was rational, they would be rationally equivalent. So they'd be in the same equivalence class, and C sub E consists of a single representative of each equivalence class. So that's the reason this holds. For any point X in set E, there is a point in the choice set C sub E, call it lowercase c, for which X equals C plus Q, where Q is some rational number. Right. So C would be the representative chosen from the equivalence class containing point X. So I can recover point X by adding to C some appropriate rational number. Okay. This first property, the fact that the difference of 2 points in the choice set must be irrational, implies if we take any set of rational numbers, any set lambda of rational numbers, the collection C sub E plus lambda, such that lambda ranges over this collection of rational numbers, is disjoint. The collection here is a disjoint collection. All right, then disjoint collection, these are translates. Maybe we can use countable additivity. So we're taking a subset this time of the rational, so you know this is a countable collection of sets. Lemma 2.6 will apply to this collection of sets, is what it amounts to, assuming measurability of C sub E. All right, so as I mentioned earlier, we took a countable infinite set of real numbers. Well, if you take a subset of the rationals, it's a countable infinite set of real numbers. Okay, the Vitali construction of a non-measurable set says, any set E of real numbers with positive outer measure contains a subset that fails to be measurable. We've mentioned this in the other videos. That means there's non-measurable sets just all over the place. Whenever you have a set of positive outer measure, it's got non-measurable subsets. So non-measurable sets are everywhere. So from here on out, when we talk measure, when we talk Lebesgue integration, we'll always have to throw in these hypotheses of measurability of all of the relevant sets. All right, let's look at a proof of the construction of a non-measurable set. I might put that word construction in quotes because, as discussed at some length in the other version of section 2.6, we got no clue what's in this set that we're about to construct that is we're going to show is non-measurable. And we don't have any idea because we've used the axiom of choice to create it. Okay. So let's see, E is a set of real numbers with positive outer measure. So that's the only hypothesis. Exercise 2.14 says if E is a set of positive outer measure, then it has a bounded subset of positive outer measure. And exercise I usually assign as homework, so it plays a role. So without loss of generality, we may as well assume E is bounded. Otherwise, we'll take a bounded subset of set E and take it from there. We'll still get subsets that are not measurable. So assume E is bounded without loss of generality. Let C sub E be the choice set for the rational equivalence relation on E, the set we were talking about above. It's that set that we'll show is not measurable. And one more time, do you know what's in set C sub E? I use the axiom of choice to create it, so I really don't know what's in it. I can describe it. It contains a representative from each equivalence class under rational equivalence on the set capital E. So that's what it is, but that doesn't tell me specifically things that are in it. So there's that distance between us and what set C sub E actually is. So that's the price of using the axiom of choice. Okay, we'll do a proof by contradiction, as we did in section 2.6, edition 3, by assuming this set, in fact, is measurable. Now, if lambda 0 is any bounded, countably infinite set of rational numbers, or for that matter, real numbers, but we're going to use rational numbers here. Since C sub B is measurable under our assumption, and this collection is disjoint, as we observed above, then we can apply lemma 2.6 to draw the conclusion that the measure of C sub B equals 0. Okay, no problems there. So far, what we're going to do is take C sub B and do some translates of it, very similar to what we did in the third edition at the same point. So if we take a translation of C sub B, let's take C sub B, translate it by lambda, where lambda ranges over any collection of rational numbers, countably infinite and bounded. So those are constraints on lambda sub 0, the set. But if we'll take the measure of the union over that collection of sets, it'll be a disjoint union, as mentioned above. So we've got countable additivity under the assumption that C sub B is measurable. Then all these translates of C sub B is also measurable. Disjoint, measurable, countable additivity. So we get the sum over those lambda values of the measure of C sub B plus lambda. We know translation invariance. The measure of the translates is the same as the measure of the original set. The measure of C sub B plus lambda equals a measure of C sub B. That is, drop the lambdas. And hey, we saw that the measure of C sub B is 0. So we sum up all these zeros, countably many. We get 0. So we've just shown under our assumption that the measure of the union of these things is all 0. Okay, we assumed set E was bounded. Well, without loss of generality, we can assume that set E is bounded. Say it's a subset of the interval from negative b to b, for some positive b. Define lambda sub 0. Okay, we just said on the previous slide, lambda sub 0 could be any collection of rational numbers. So let's take it to be the collection of rational numbers between negative 2b and positive 2b. All right, that's a countably infinite bounded collection of real numbers, actually rational numbers. So we're good. What we had stated above held for any countably infinite bounded set. So here's a specific one. So we're defining now lambda sub 0 to be this collection of rational numbers. Lambda sub 0 is bounded. There's the bounds right there. It's countably infinite because there's so many rational numbers in an interval. All right, let x be any point in the original set E. Then there's some C in the choice set such that x equals C plus Q for some rational number Q. That is, x and C are in the same equivalence class. Remember, the equivalence class is partitioned up set E, and we have chosen some representative of the equivalence class containing x and put it in the choice set. Call it C. Call C the choice from the equivalence class containing x. So we've chosen that one to represent that equivalence class, if you like, in C sub B. That means x is rationally equivalent to C, so x equals C plus Q for some rational number Q. Now, x and C both belong to this interval. I mean, they're both elements of E. X is an element of E, and so is C. So they're both in the interval negative C to C. X we've expressed as C plus Q. So x itself also is in the interval from negative B to B. So x equals C plus Q. That's in C sub E plus lambda for some lambda between negative 2b and 2b. Think of it like this. Let's see, we could maybe have x be close to negative b and c be close to b. How far apart could x and c be? Up to a distance of the length of this interval, because x and c itself are both from this interval. Maybe over here, both from this interval. How far apart could x and c be? Up to 2b units apart. So this rational number might have to be up to size 2b, or negative 2b. So that's the reason that we know the rational number lies in here. Since x was an arbitrary element of E, and we just showed that x is in C sub E plus lambda for some lambda in this set here, capital lambda sub 0, then we've shown E is a subset of the union of these translates of the C sub E's. Now we got into this assuming the outer measure of E was positive. And we've seen on the previous slide that the measure of this union equals 0. So we got a problem here. We've got a measure, a positive measure subset of a measure 0 set. So that's a contradiction, specifically by monotonicity. We have the outer measure of E is greater than 0. 0 is less than the outer measure of E. Yeah, you were told E has positive outer measure hypotheses. We've got E as a subset of this union. Okay, monotonicity tells us then the outer measure here is less than or equal to the outer measure here. And we showed on the previous slide that the outer measure of that union was 0 under the assumption that C sub E was measurable. And so we've got 0 is strictly less than 0. There's your contradiction right there. So the assumption we made upstairs, and that assumption was that C sub E is measurable, that must be false. And so C sub E is not measurable. There's your non-measurable set. Read through or watch the video for section 2.6, where the non-measurable set in the third edition is constructed. We call it set P, and it's quite similar to what we're doing here, conceptually similar. We've thrown the boundedness in here, and we did something a little bit different there. But the ideas behind this is axiom of choice, and this is Vitali's construction. So we know there exists a non-measurable set if you accept the axiom of choice. This is a repetition of some material in the notes for the third edition. Claim is there are disjoint sets of real numbers A and B for which the outer measure of the disjoint union is strictly less than the sum of the outer measures. See the video for section 2.6, edition 3, for a tirade about how messed up this is. Yeah, well, you're taking a set, you're just breaking it into two disjoint pieces, and it gets heavier. It gets a larger outer measure when you just break it in two. Yep. That's a consequence of the axiom of choice. Don't go weird on it. Hey, outer measure is not finitely additive. We got to have finite additive to set up our integration theory. So that's why we're considering only measurable sets where this kind of thing doesn't happen. But here is, I'd like to say, an explicit example, but it's not because it's rather indirect proof, of two sets where the measure of the disjoint union is strictly less than the sum of the measures. Well, assume to the contrary that we get equality. We've got subadditivity, we get less than or equal to in general. I think we'll comment that shortly. But suppose that we had equality for every disjoint pair of sets A and B. But then if we go back to the Carathéodory splitting condition, which said the outer measure of A, that would be the outer measure of A intersect E, disjoint union with A intersect E complement. So this was how we had split things. This would be a union of two disjoint sets. If this equality holds, then we get the sum of the measures of these two things. And that would imply, this holds for any subsets A and E of the real numbers, that would imply the Carathéodory splitting condition is satisfied by all sets of real numbers. That would imply there's no such thing as non-measurable sets. All sets are measurable. Well, that's a contradiction because we just, quote unquote, constructed a non-measurable set. That set C sub E, the choice set. So there must exist some sets that violate the equality. How do you violate the equality? We could have greater than or less than, I suppose. Well, subadditivity tells us that we would have to have the outer measure of A disjoint union be less than or equal to. Subadditivity, proposition 2.3, one of the first things we did with outer measure. We've got subadditivity for outer measure, so I do know that this holds. So if we violate equality, then it must be with a strict inequality of that sort there. And that establishes the existence of such sets very, very indirectly, though. And that's the material of this section. Again, I recommend taking a look at the proof from the third edition and the video for the proof in the third edition of what we have here. I go on and rant a bit about how messed up it is that this kind of thing occurs, but it lies totally at the feet of the axiom of choice. Without the axiom of choice, you can't demonstrate the existence of a non-measurable set. And there's some references to the result on that given in the other video. So there you go in terms of non-measurable sets. We'll move on, maybe look at the Banach-Tarski paradox as a little supplemental topic. And I would like to know how many non-measurable sets there are and how many measurable sets there are. Turns out there's lots of both of them. And we'll go through an argument to establish that after we look at the Cantor set in the next section. I'll see you there. Have a nice day.